All right, so last class classes, I should say, we looked at Newton's first law and drawing free body diagrams. There's actually three Newton's laws, so we're going to do the second and the third one here. The second one's probably the most famous law because it follows the first law, because the first law, again, is if the net force acting on an object is zero, then the thing is not going to move. It's the property of inertia. So something's at rest, not moving, it wants to stay at rest. And if it's moving, it doesn't want to stop or speed up. All right, now, the second law is if that does not happen, where if the net force is not zero, then the object accelerates. Accelerates is a nice way of saying changes speed in the direction of the force. Now, there's actually a formula here, is that what we have is F net, our net force, which again is a vector, it's got direction on it, is mass times your acceleration. So again, where it matters what size you've got, so where m is mass, and a is the acceleration. So it tells you how much it changes the speed of the objects we're talking about. So, for example, example one here, find the net force on a 5 kilogram object that accelerates at a rate of 3.8 meters per second squared east. All right, so a couple of things. Again, I always like to write out what I know and what I'm trying to find out. And it says find the net force. So I'm looking for F net here. All right. The mass, again, not to be confused with weight, which we looked at last class, is 5 kilograms. All right, and our acceleration is equal to that 3.8 meters per second squared. Again, it's east. Now, if our object is being accelerated east, well, that means our net force is going to be east. All right, so I'm going to use my formula, F equals ma, or F net equals ma. And so I have my 5 kilograms, all right, times my 3.8 meters per second squared, per second squared, and again, east. Go. All right, and then if I multiply those numbers, my 5 times my 3.8, I end up with, let's see here, grab my calculator. Oh, right on a nice round number of 19. And again, when we're talking about forces, we're talking about newtons, the big N. And again, because we're accelerating east, that means our force was pushing us east. And there we go. All right, so when the net force is not zero, then the object is changing speeds. Again, in our first law, when the net force was zero, then the speed doesn't change. A little bit different. All right, let's see here. Go the other way here. What is the mass of an object that experiences a force of 480 newtons forward and accelerates at a rate of 1.5 meters per second squared forward? Again, you can see that because our force is pushing forward, well, we're going to accelerate forward. All right, so this time again, we're looking for mass this time out. All right, now our force, we're both in the same direction here. We got 480 newtons forward, put an F there. All right, and what else we got? Acceleration. So we got our A is equal to 1.5 meters per second squared. And our direction here is forward. All right, so as I mentioned, we're going to use Newton's second law here. It's F net equals ma, but mostly you just go F equals ma. All right, now the direction's in the same spot, so we don't have to worry about that, which it has to be. All right, so substitute into my formula. I got 480 is equal to, we're trying to find the mass, right? And our A is 1.5. Now, normally when we have, unless I'm just adding a step here, but if I have m times 1.5, usually we go 1.5 times m. It's usually math or science, how you write it. All right, but I want to get the mass by itself. So I'm going to divide both sides here by my 1.5 to get m by itself. All right, and so those 1.5s divide each other out. And so if I take 480 and I divide it by 1.5, what do I end up with here? I get, 320. And again, because we're in standard units here, kilograms. Here we are. Any questions about that so far? Nothing. All right. We're going to move on to the third law. This is maybe something you've heard before, but for every force, there is a reaction force equal in magnitude, but opposite in direction. For example, jetpacks in space. If you want to go to the left, you shoot your rockets to the right. Or if you want to go up in space, whatever up might be, you shoot your rockets down. All right, so for every force, there is a reaction force. And another way that I do it is when I'm in school, can't do it in my room here, I'd fall, is using office chairs. Often I'll push off my desk to make myself go backwards. So I'm applying a force to the desk, but then the desk is applying a force back on me. And that's why my office chair gets to move. Now, classic example of this third law is example 1 here, where Travis, 75 kilograms, is about to dock his canoe, 30 kilograms. He jumps off the canoe towards the dock with his foot, exerting a force of 155 newtons on the canoe. What is the magnitude of the acceleration of both Travis and the canoe? So just to kind of give you a picture here of what we're looking at. And again, you can see what a great artist I am here. Here's my canoe. There we go. There's Travis. Call this guy. All right, there we go. And Travis pushes off the canoe, so he applies a force to the canoe of 155 newtons. Now, here's what happens, is that the Newton's third law is that the canoe reacts by pushing back on Travis with 155 newtons. Now, here's what can happen, is that I can look at how Travis accelerates because the boat is applying a force on him of 155 newtons. Now, Travis has a mass of 75 kilograms. What we can do is, using Newton's second law, see how these laws tie in together, we can find the acceleration of Travis. All right, so again, I'm going to use that second law that we just went through, F equals ma. The force is 155 newtons. We know the mass this time of Travis, which is 75, and we're looking for the acceleration here. Now, whoops. All right, and so I'm going to divide both sides here to get A by itself by 75. 75 on this side. All right, and my acceleration, let's see here. I take 155 and I divide it by 75. And it's going to accelerate at a rate of again, going to 2 decimal places, 2.07 meters per second squared. Now, we can also find the acceleration of the canoe. And so the canoe, because of Newton's third law, Travis pushed on it with 155 newtons. Right, but the canoe has a mass of 30 kilograms. And we're going to find the acceleration of the canoe. All right, so again, using the formula we have for Newton's second law, because we do have a net force here. All right, we're assuming there's no water resistance. But so I'm going to plug in here 155 newtons for my force. My mass is 30. And again, we're trying to find the acceleration. Oh, just like I did in the last formula. Same idea, I'm just using a different mass. And so I'm going to divide both sides by 30. And so now what we're looking at is my acceleration is equal to 155 divided by 30, which is 5.17 in standard units here, meters per second squared. So in this situation, the Travis is speeding up at 2.07 meters per second squared, but the Canoe is speeding up at 5.17 meters per second squared. Now, depending on how close Travis is to the dock, because the Canoe is going to take right off on him, he might end up in the water. And so that's something to watch out for in Newton's third law. This won't be because mass is such a big deal. If you're on a large boat, your acceleration of the boat was going to be very, very small compared to you. But in this case, because you're dealing with a Canoe and Travis is over twice the size of the Canoe, there's an issue here. Now, what I want to show you is how that could apply. Just give me a second here.